So we're going to look at the review, and we are going to start with question 10. For questions 1 through 9, those were in the part 1 video. So if we look at question 10, what I have done over to the right is I have broken down what each of the pieces of the equation are. So we're talking about our compounded n number of times formula. So the A, remember, is your final value, your P is your starting value, your R is your rate as a decimal, your N is the number of times things have compounded, your T is the time, and in this case it would be years. So the first one there, my 0.035 divided by 12, that is the monthly percentage change, because if I know that it's happening monthly, then if I divide that rate by 12, because that's an annual rate, that would be the monthly percent change. For the second one, the only difference between the first and the second is that 1 plus. So that's what's inside of there. That would be the monthly growth factor. Remember, we always add 1 onto that. B, what does that NT stand for in our formula? That's the number of times that it compounds in T years. So 12 times 6 would be the number of times, monthly, 12, that it would compound in 6 years. And then our fourth one is 1 plus R over N to the N. So that was, you'll notice the 12s match there. That is the annual growth factor, and that will always be the annual growth factor for a compounded so many times per year type problem. And then the growth rate is going to be the final one there, because that is going to be our growth rate for T number of years. So just if you write down that formula, you can then write down what each of those things stand for. Now remember, for the test, you may have a note card. You may have a note card with any of these things on there. There are some formulas up on the board for some of the graphing stuff that you are welcome to also write down on your note card. The note cards you may write on the front and the back. It's a 3x5 note card. If you don't have a note card, feel free to cut a corner out of a sheet of paper, make it 3 inches by 5 inches, and you got it. Now we're going to move on to question number 11. So I'm going to scroll fast here and then we'll stop. Okay, so we're still going to use that compounded n number of times formula that you see on the right there. In my particular case, my P is 8100. My R is that 4.8% written as a decimal, move it 2 places to the left, 0.048. I divided by 2 because it semi-annually means twice per year. And then the power is 2 times 14. So what I like to do is you might want to write out what you know it is on a paper. Make sure your preview matches that. I made iMath do most of the work for me for these problems. So you'll notice that I have entered that exactly as I would have had I just plopped it into that formula. So there is question 11. Let me get question 12 green here. Now, just a second. I lost it. There we go. For question number 12, it says that we have a formula. Each one of those said compounded continuously. So please make sure you're using that PERT formula. Write that down. Write the word continuously next to it. The first one here I've written out, our starting value, 4,500. E to a power of. Now put that in parentheses, that rate, 0.033, that's that 3.3%, times 13 years. And then I just changed it accordingly for B and C. For B, it's $700 at 3%, and C, it's $2,100 at 7.4%. Each time we're using 13, each time we're using the PERT formula. So that is question number 12. Now let's move to question 13. I'm going to fill it all out, get it green for you, and then we'll talk about it. Now, it says, what is the annual growth factor? So the formulas you want here are, this is for a number of times compounded continuously. We wrote that down, if you wrote that down when we were doing question number 10. The one we didn't write down is, what is the annual growth rate for something that is continuous? So it's just e to that rate. Here, remember, that's 1 plus r over n. To the n is our annual growth rate. So you notice I've just entered those things. So in A, I've entered 1 plus 0.087, because they're all using that 8.7%, divided by 2, because it said semi-annually for this first one, to a power of 2. This one, you'll notice I changed it to 12 because it was monthly. So the 12 went there and the 12 went in the power. And this is a continuous problem, so we have to use e to that rate. Remember, the only main difference is if your something is decreasing. For our continuous power, please use a negative rate. If it's going down, use a negative rate. That's one of the main things to remember. So that is question 13. Let's move on to question 14. I'm going to get everything green and then I'll show you. So we're just using the PERT formula for this. Now, the reason we know that is because it says at a continuous percentage rate. So please make sure that you have a note on your note card that the PERT formula is used for a continuous percent change. So our formula, in my case, it's f of t, is the starting value, 32. They didn't say to put the million in. See how it says in millions? Times e to a power of our rate, 0.016, written as a decimal, times time. I put that entire thing, that RT, in parentheses so that it doesn't mess up. And then B says that what's the population in 2019? So this formula starts in 2000. In 2019, that's 19 years later. So take out your T and replace it with a 19. I let iMath do the work. And then the annual growth factor in this context is just e to that rate. So e to the power of 0.016. And so we know each year the population is 1.016 times as large as the population in the previous year. So that is a little bit about question 14. Now let's move on to question 15. Let me get everything green there and then we'll discuss. So some formulas you might want to write down on your paper. This formula, there's two of them right here. You could put even an equal right there. Log base 5 of x plus the log base 5 of y. Remember, it's just the log base 5 of x times y. So in question A, I have just put the log base 5 as log underscore 5, and then in parentheses, I just multiplied those things since each one of them was positive. So you'll notice I just put 5 times 100 times 35. I let iMath do the work. Same thing for B. That would be the log base 4 of 1/4 times 1 over 28. I let iMath do the work. I don't know. Here's the one that's different. See, we have an extra step first. You first must move the 3 onto the 14. So that's the rule you see right here. Please write this rule down, that n times the log base 5 of x is the same as the log base 5 of x to the n power. So it's very important to remember to take any front coefficients and make it a power. So first I put the 3 onto the 14, as we see here, and then I notice it's an addition, so then I'm going to multiply them inside of one logarithm. So my final answer is log base 6, so log underscore 6. of 14 to the third times 5. And then make sure your preview is what you think it is before you hit submit. So there's question 15. Let's move to question 16. Just a second here. Just trying to get it to turn green without missing something here. There we go. So the rule that you want to have here, you can barely see it, but let me read you this rule. Another rule is if you have the log of x minus the log of y, it's the log of x over y. Ignore that little line there. It's the log of the fraction x over y. Okay. So let's talk about some things we want to do. Okay. So you'll notice that the 6, I moved on to the x. See, it's an x to the 6th. The 1/6, I moved on to the y. The 3, I moved on to the z. All of the positive stuff is in our numerator, my x to the 6th. The negative stuff, y to the 1/6 and z to the 3rd is in the bottom. I separated them with parentheses so that I could tell definitely that they showed up in the bottom. You can use the little box feature that has that equation editor that you can use. Feel free to do that. Now, I wanted to discuss part B, okay? See how this -2 is in front of the whole parentheses? Distribute the -2 in. See how I distributed it? And I got the log of x minus 2 log of y minus 6 log of z, okay? Then I put the powers on. 2 went on the y squared. 6 went on the z to the 6th. And then all the positive stuff, so the x goes on top. The negative pieces, y squared and z to the 6th, goes in our denominator. So that is a little bit about how we condense something. So that is question 16. I'll leave that there so you can get yours hopefully all lovely and green. Now I'm going to scroll to question 17. I'll make sure those all turn green and then we'll discuss those. Here's 17. Now the first one, in the instructions it says, if the expression cannot be expanded, write n. Now the reason a cannot be expanded for me is because of the fact that it is a subtraction in a logarithm. Remember, we can only expand a multiplication or a division. There is no, it's two terms added or subtracted. We can't separate that. But b we can. All we're going to do is we are going to take the log of the top minus the log of the bottom. Now I do have c over here to the right. I have first I would write it like this. See, it's just the log of 3 plus the log of 8 at 8. But it will mark it wrong if you leave it like that. Remember, it says in the instructions, do not contain the logarithms of products, quotients, or powers, because we got to remember that 8 needs to drop down in front. So you see how I put the 8 in front of the log of a. So be careful with that, okay? So that is how we expand. So that is question 17. Now let's move on to question 18. Let me get question 18 turned to green there, and then we'll talk about that. There we go. Now, another thing you might want to add to your card is what we see right here. Remember that a radical can be rewritten as a fractional exponent. The power goes on top. If you don't see a power, put a 1. The index goes on the bottom. Put an m. If you don't see the index, it's always 2. So my fraction on top, if you think about powers, that's an x to the 1/4 and a y to the 6th. So I drop the 1/4 in front of the x and the 6 in front of the y. Remember, we're subtracting because it's division. Let's talk about the powers we see on B. That would be an a to the 1/2 power, x to the 5th, y to the 7/6 power. Okay, so when I did it, my top one, my 1/2 drops down in front of the natural log of a. We're subtracting the x to the 5th, but the 5 drops down in front. We are subtracting the y to the 7/6, but the 7/6 dropped down in front. And you can see how I have, this is the first problem right there. I'm sorry, that's part A. So the 1/4 dropped in front, the 6 dropped in front. We're subtracting because it's a division. So there is question 18. Question 18. So that's the row you might want to add to your card in black right there. Let's move on to question 19. The 19 is a nice one. It's nice and green right there. So any of the factors on top, you'll notice the x and the y are both positive. I dropped their powers down in front, so 21 log of x plus 39 log of y. And then I have subtracted the z that's in the bottom, dropped its 15 power down in front. So that's a nice one. There is question 19. Let's move on to question 20. I'm going to turn everything green here, and then we'll talk it through. Okay. Now, for question number 1, it says that the U.S., I'm sorry, some of the questions cut off, but you should be able to read yours. It says the U.S. Census Bureau determined that from 1910 to 2010, the U.S. population increased by approximately 1.5% each year. The 13th U.S. Census conducted in 1910 determined that the U.S. population was 92.228 million people. What is the 6-year growth factor? So they told us that from 1910 to 2010, the each year growth rate was 1.15. So if we take that, or 1.5, I'm sorry. If we take that 1.5 and add it to 100, that's 101.5, or the decimal 1.015, take it to the 6th power. So if we want to know the population in 1916, you're just going to take your starting value, 92.228, times that 6-year growth factor, because it started in 1910. We went to 1916, 6 years, you would go 6. If you need 7 years, go 7th power, 8 years, whatever. Now, what's interesting is part C, you'll notice it goes from 1942 to 1948. We don't have to calculate that 6-year growth factor. Again, we always know that it's consistently 1.015 to a power of 6. So you'll notice I've done that again. Now, I want to talk through part D, okay? Because D is the hardest one on this sheet. And then there's some in question 21 that kind of follow a similar idea. I've done the math over on the right here. Let's talk it through. So I want to know when this formula with T missing, so my starting value 92.228 times our growth factor of 1.015 to a T will equal a population of 144.37. Now, anytime you're looking for the time, it's always going to be the same. We're always going to end up being the natural log of the final value divided by the starting value over the natural log of the base, or the growth factor. Okay, let me say that again. We always end up with the natural log of the ending value divided by the starting value, all divided by the natural log of the base, or the growth factor. Because watch what we have to do every time. We're always going to divide off the starting value. We get this fraction. We're going to put a natural log on both sides. The t will drop down in front, and then we have to divide this natural log number off. Now, what I did was I put that number here, I put this here to let IMath show me the number. And the number was 30 point some. So if the answer is 30, if this answer is 30 years and they want to know what year did it happen, so it started at 1910. If I add 30 years, I get 1940. So again, this is a very hard process, okay? It's always going to be the natural log of the final value, which in the formula was A, divided by the starting value in the formula was P, over the natural log of our base, or our 1 year growth factor. Okay, so that is the hardest part of this particular problem, part D. So I'll give you some time to get yours working, and if you have any questions, let me know. Let's move on to question 21. I'll get those all turning green. Now, this one, I use that same formula again and again and again and again, okay? Same thing, the natural log of the final value divided by the starting value over the natural log of my growth factor. So look at this first one here. I want to know when is it predicted, when, time, that we will be at 9,850 people. So it's the ending, 9,850, divided by Linwood starting, 9,450, all divided by the natural log of the growth factor, 1.24. Now, I let IMath do that math for me. I got 0 point something. So the year 1995, it wouldn't even have got into 1996. I just added this front 0 on, and that's why I got 1995, 0 plus 1995. For B, so let's think about what we're going to put in. I have it right here. The natural log of my ending, 13,400, divided by my starting, 9162, all over the natural log of the 1 year growth factor, 1.14. I got 2 point something, so 1995 plus 2 more is 1997. And then I set it up again. I let IMath do the work. And this bottom one, I got 1 point something, and so I added 1 on to 1995 and got 1996. So this one I would do 11,000, the natural log of 11,022 was 0, divided by the natural log of 12,896, all over the natural log of 0.89. And that's what you add on the whole number to 1995. So that one's a pretty complicated one, a little strange, but you do the same thing each time. Let's look at question 21. Let me get that all green and lovely. Boop. I think I did it so quick and then moved away. Oh, I think I got it. Okay, there we go. So it says a 10-ounce sunflower is planted in a garden, and it's a continuous growth rate, daily continuous growth rate at 8% or 18%. So be careful. I'm sorry, that should say 0.18, 0.18. I did rewrite that incorrectly. It's right up there, but I'm sorry. Okay, so initially our formula for this, starting value, 10. E, because it's continuous, we have to use PERT, to a power of 0.18 t. Okay, so that is my formula. So when will it be 31 inches tall? We have to know when is the formula equal to 31. And so you always end up doing this. It's always the natural log of the fraction, the final value divided by the start, so 31 divided by 10, all divided by the rate. So in this case, mine would be 0.18. So you see, oh, it's 0.18. And then the only difference between B and C is at B, we wanted 31. So just take that 31 out and replace it with 167. So that is question maybe 21. Oh, actually, that was question 22. Now let's move on to question 23. So it says we have a population of Italy in 2019 was approximately 60.5 million, and it's been increasing continuously. So that tells us we have to use the PERT formula. So let me fast forward here and show you the answers, and then we'll talk about how we got them. I think they're green. Was there a D? There we go. Ooh, sorry. I recorded this earlier and it didn't have any sound, so I had to kind of backtrack. So our first one, our function, use your starting population, 60.5, and then e to a power of 0.0163 times t. Put that power in parentheses. Then for B, how many years until the world population is 68? Here's the formula we're going to use to solve. You always have to divide 68 by your starting 60.5. See where it's the natural log of 68 divided by 60.5? All divided by the rate. Because we're going to take that natural log, and when we take the natural log of E, you just get that 0.0163. Okay? And then that's what when would it be 68? You'll notice I have 68 there. C, when will it be 88.5? I put 88.5 where the 68 was. And then the final one is a little tricky one. When is it going to double? So just think about, when is it going to double? What's the double? So double of 60.5 or 60.5 times 2 is 121. So you'll notice I put 121 in the same spot. For B, I put 68, and then C, I put 88.5. I just use the double amount, 121. So that is your review. Please study. Remember, you can have a note card with some of these formulas on there. You can write on front and back. It has to be a 3x5 card. If you don't have a 3x5 card, get a ruler, cut a corner of your paper out that is 3x5. So there you go.